So try to find more information on this, you may get the answer. So screen, is it visible, Ganesh?
Yes, sir.
So we'll straight away go with the next numerical. Investigate the stability of negative feedback system whose open loop transfer function is given by g of s into h of s equal to 100 divided by s plus 1 into s plus 2 into s plus 3. Okay, 100 divided by s plus 1 into s plus 2 into s plus 3. So I will mark the poles zeros of the open loop system, that is minus 1, minus 2, minus 3. Then I will consider the entire right half of S plane for mapping. I will name it as A, B, C, D, same as the previous example. So then we have to find out the number of poles lying in the right half of S plane. So there are no open loop poles which lie in the right half of S plane. So P is equal to 0. Then directly start mapping path AB.
Sir, in yesterday's class, the numerical that we did, when you showed the mapping from S plane to GH plane, you drew a small semicircle near the origin. Why is that?
Just hold on. Just hold on. I'll answer. Yes, somebody is asking doubt. Please continue.
Sir, I was asking in yesterday's numerical, when you were showing the mapping from S plane to GH plane, you had drawn a small semicircle near the origin. Why is that?
Small semicircle near the origin. For previous example?
Yes, sir.
Okay, let me get back and check out. Just a moment. Yeah, where did I draw the circle? Here?
Yes, sir. That one.
It's not semicircle, it's the range of theta I am trying to indicate. I should have put arrow mark here. It's not a semicircle, it is a straight line. Okay?
Okay, sir.
This is the range of theta. So I have kept 5 to 6 color pen, but in a hurry I forget to indicate a different color. So there is no semicircle as such, it is theta only. Clear?
Yes, sir, got it.
Okay, fine. Then we'll come back to today's numerical. If anybody has such doubts, please try to clarify without fail. Fine. So in the today's class, we consider another different numerical, which is given by hundred divided by s plus 1 into s plus 2 into s plus 3. So p equal to 0, then let us map path AB. So path AB we substitute as equal to j omega. Fine. In g of s, h of s, and then we find magnitude of gh for path AB, then phase angle of gh of j omega for path AB. So numericals are very, very easy. Without knowing the prerequisite, you can solve. That is also one of the beauty of Nyquist plot. But let us not do it blindly. Keep the concept in mind. So magnitude is 100 divided by omega square plus 1. Okay, omega square plus 4, omega square plus 9. Because we are directly making substitution of s equal to j omega here. Then phase angle is, numerator phase angle is 0. Denominator phase angle, when it comes to the numerator, it will become negative sign. So tan inverse of omega by 1 minus tan inverse of omega by 2 minus tan inverse of omega by 3, it should be just a typo. Please correct it later. Then we go for substitution of each highlighted points AB. So at A, omega tends to 0. and limit of gh of j omega as omega tends to 0 is 100 divided by 0 plus 1 into 0 plus 4 into 0 plus 9. So if you take the square root, it is just 2 into 3. So therefore magnitude is 100 by 6. Then when you take the angle, it is 0 minus tan inverse of 0 because we are substituting omega equal to 0. So all zeros, so angle is 0 degrees. That is path point A dash, first point. Then second point is as omega tends to infinity, that is point B. So when omega tends to infinity, we have a omega in the denominator, so magnitude is 0, whereas phase angle is minus 90, minus 90, minus 90. Okay, tan inverse of infinity will get 0 magnitude and 270 degree with a negative sign. So let me represent this particular path on the GH plane. Okay, 100 by 6 is approximately 16.66. So no need to, it's not required to draw up to scale. More importance for this numerical is given for the shape of the plot and calculation of some key parameters. So please remember, Nyquist plot, even if you don't draw it in the graph sheet in the exam, that is well and good. But some calculations will remain same and the shape has to be correct. Shape of the plot has to be correct. Okay. So this is A dash. A dash is 100 by 6. Okay, with 0 degree line. So 0 degree line is of course real axis. So first point is A dash here. Then it ends at 0 magnitude. Okay, with a phase angle of minus 270 degrees. With a phase angle of minus 270 degree. So that everyone has to remember. Minus 270 means it starts from here, then ends at minus 270 degree line. Because there are 3 poles. This we have already done in polar plot. The path AB is done, then path BCD. The path BCD we have to substitute S equal to limit as r tends to infinity because this is a semicircle with the radius as infinity and phase angle changing from 90, 0 and minus 90. So I will substitute this in the given transfer function. So that is 100 divided by limit r tends to infinity, common for all the 3 terms. So r into e raised to j theta plus 1, r into e raised to j theta plus 2, r into e raised to j theta plus 3. Fine. So r is much greater than 1, 2, 3 because r is tending to infinity. Therefore, we can write r, then e raised to j theta, e raised to j theta, e raised to j theta. So what we get is 100 divided by r cube into e raised to j3 theta. 100 divided by r cube or yeah, there is again a typo. So anyhow, 1 divided by infinity is 0, so it doesn't matter. Whereas the phase angle is 1 divided by 3 theta, when it goes to numerator, it is minus 3 theta. So again it should be noted that the S-plane part is changing from 90, 0, minus 90. So you substitute all these 3 values in minus 3 theta. So minus 3 into plus 90. The first point is minus 270. Second is 0 into minus 3 theta, 0. Third is minus 90 into minus 3 theta plus 270. So it's a 0 magnitude, therefore it is origin. So there is no any curve, anything that we need to draw. So origin. So one thing you can observe is from path A to B, then the path BCD. So there is a continuation. So you can also check this continuation clearly that the phase angle has been ended at minus 270 for path AB. Then for path BCD, it has started from minus 270. Okay, this is just a cross verification. If you end up with say some wrong answer, minus 270 here plus 270 here, you can cross check your calculation. So it started from 0 degree, ended at minus 270. So the next path has to start from minus 270 and it ends at plus 270. This is a continuity of the mapping. Then path DA is very much similar to path AB. So we write a comment saying it is a mirror image of path AB. Therefore, directly draw the mirror image of the existing plot. Okay. So A dash to B dash, B dash to BCD dash, then D dash to A dash. Fine. So this is the Nyquist plot. Our next job is to check the closed loop system stability. Closed loop system stability. So what is the closed loop system stability here? Can anyone say that? Comment on stability. Anybody has any answer? So for that, we should know what is the value of this point, the point where it intersects with the minus 180-degree line. So if we know this value, then we can use the formula of Nyquist criterion and then we can comment on the stability. So let me call this point as M, and depending on the value of M, value or magnitude of this M, number of encirclements around minus 1 plus J0 can be found. So if we know M, then we can find the number of encirclements. So how? If the magnitude of this M is greater than 1. Okay, suppose for example, if this M lies somewhere beyond minus 1, whose magnitude from the origin is greater than 1, then obviously there will be encirclement. Okay, we don't know yet whether it is encircling minus 1 or no. Okay, because we are making approximation in mapping, we are not doing any point by point mapping. Therefore, this is some additional task for us to check whether it encircles or no. So I will call this point as M, and depending on the magnitude of M, I will make a conclusion of encirclement. So if M is greater than 1, then obviously there are encirclement. Okay, if M is greater than 1 means this curve is passing beyond minus 1. And similarly, if M is less than 1, if the magnitude of M is less than 1, then this curve is not passing around minus 1 point. Fine. So that is what we need now. So the question now is how to find M. How to find M. So there is one hint. So one hint is at the point M, the Nyquist plot curve cuts the minus 180-degree line. Okay. So this approximated curve, which is starting from A dash and ending at minus 270 degree, it has to pass through minus 180 degree. So it will cut at minus 180 degree line. Okay. So at point M, Nyquist plot cuts the minus 180 degree line. That is the phase angle of the curve in the path A dash B dash, or phase angle of the curve A dash B dash at M is minus 180 degree. Please understand. So this A dash B dash curve is a solid pink color. It is cutting at minus 180 degree line. So how do we got this curve is only based on the approximation of path AB from S plane. So that also means this is how our plot varies with a variation in omega and with a variation in with a variation of omega. This is how our plot has gain and phase angle. It's somewhat similar to polar plot, you can say. So when it proceeds at this particular point, we assume that the phase angle of the curve is minus 90 degree. And when it proceeds further, we assume that the phase angle of the curve, phase angle of the curve or the phase angle contributed by the OLTF is minus 180 degree. And at the end, when omega is infinity, we assume that the phase angle contributed by the open loop system is minus 270 degrees. Fine. With zero magnitude. So I would like to give some additional information. Okay. Just a conceptual practical interpretation of variation of omega equal to 0 to infinity. If you understand, that is well and good. So when I say omega is 0, it means the frequency applied to the open loop system is 0. Okay, or in general assume the frequency applied to the system is 0. So it is as good as a DC input. Fine. So when you apply a DC input, there is no question of phase angle difference at all. Fine. Because you are applying a 5 voltage input, you cannot expect a phase angle difference at the output because it is not a sinusoidal function, sinusoidal input. Therefore, at omega equal to 0 or frequency f equal to 0, there won't be any phase angle difference at the output side, which is highlighted at this point. Similarly, you imagine that you are applying a frequency of 50 kilohertz to a system. Suppose if that is a pendulum, okay, can you imagine how it behaves when you apply 50 kilohertz of frequency? Okay, it will not follow the input exactly. There will be huge delay in following the input signal because of the inertia of the system. So that's why this high delay has been uh, occurred at that particular system. So this is in general for all dynamical systems. At high frequency, they will always have a huge delay. So this is what you can interpret from the omega equal to 0 to infinity part. Fine. Then path BCD, it's a complex plane. We cannot realize any practical signal from this part. So it ultimately ends up with a dot on the system mapping. I mean the mapping on GH plane. So at this particular frequency, at some particular frequency, the phase angle difference of the OLTF has occurred to be minus 180 degrees. So to know the m value, first we need to find the frequency at which minus 180 degree occurs. And for that particular frequency, you calculate gain from the origin. So if that gain comes out to be greater than 1, then it means curve is enclosing the minus 1 point. If that gain comes out to be less than 1, then the curve doesn't encircle the minus 1. So that is the ultimate conclusion. So now we are using this phase angle expression and we equate it to minus 180 degree to know that for what omega this is minus 180 degree. Okay. So solve for omega and then for this omega. Okay, for this omega, find gain. Find the gain. And that gain will give us magnitude of m. So how to solve this? The basic trigonometric identity. Everyone can do it yourself. So tan inverse of A plus tan inverse of B equal to tan inverse of A plus B divided by 1 minus A. So the same identity I have used and I have simplified this. So let us see what answer I will get. Okay, so tan inverse of 180 will become 0. So denominator will get 0. Only the numerator will be equated to 0. So solve this for omega. Final equation for omega. So what values we get? Ultimately, so omega if you take common, one of the answer you will get as omega equal to 0. One of the solution for this equation is omega equal to 0. Which means at omega equal to 0, you will get minus 180 degree. Which is not true. So what is the other solution we get? So other solution is simplify this. You will get omega square equal to 11. Okay, 9 plus 2 will get 11. So this is possible. Second one is possible. First one is not possible. Or omega equal to square root of 11 radians per second. So now at square root of 11 radians per second or something 3.33 radians per second, let me calculate the gain. So how to get the gain? So gain equation is here. Directly substitute square root of 11 here and calculate the gain. So for this omega, that is square root of 11, let me check the gain. That is 100 divided by square root of 11 square is 11. So 11 plus 1, 11 plus 4, 11 plus 9. So ultimately we get 1.666. So my gain m at a frequency where it is meeting with the minus 180 degree line or negative real axis, this gain is 1.66, which is greater than 1. So will there be any encirclement around minus 1? Anyone say that? Anyone wants to say answer? Will there be encirclement?
Yes, sir.
Yes?
Yes, sir.
Amog Mishra? Are you
Yes,
following?
sir. No, sir.
Why? What
I'll
exactly
have
you
to
are
believe
missing?
it, sir. I don't understand this, sir.
What actually you are missing, you feel?
Sir,
What actually you are, I mean, missing to understand? Is it you have to go through the previous videos once again?
I'll have to go through, sir. I don't understand this. I don't know. I'll have to read.
Okay, fine, no problem. Uh, Karthik Patil.
Sir, am I audible now?
Yes.
Hello, sir. Yes, sir. Sir, I missed two class. I think. Means I was in the class, but I lost connection. That's why
Okay,
I have to
okay.
read.
Go through the previous videos.
Yes, sir.
Priya R.
Sir, I have to go through the videos again, sir.
Yeah, please go through it without fail.
Yes, sir.
Okay, then Mohammad Kamruddin. Mohammad Kamruddin. Nandan, yes. Are you following?
Yes, sir.
Okay, then Shashank Karsi. Shalini Gupta.
Yes, sir.
No doubts. Shalini Gupta.
So yesterday I missed the class. Like I was present, but I lost connection in between.
Okay, okay, fine. Okay, Siri MS.
Yes, sir. I'm understanding.
Fine. So if anybody is not able to understand, don't worry. I have given everything in the previous video lectures. Go through it and come back to this. It's easy, not as difficult as you think. The equations and all, if you look at this suddenly, those who were not there yesterday, you will feel like something new, some rocket science has been done, but it's very easy. Fine. So the ultimate conclusion is there is encirclement around -1. There is or there are. Let us see that. Therefore, the Nyquist plot n circles -1 plus j0. So look at this now. So -1 lies within the circle. Therefore, this is first encirclement. Okay, this is first encirclement. This is second encirclement. So there are two encirclements. That is n equal to 2. Therefore, p equal to 0, z equal to n plus p equal to 2. So it means there exist two closed loop poles which lie in the right half of S plane. Therefore, closed loop system is unstable. Okay, so let us look into MATLAB part. A quick cross verification for self satisfaction. Ganesh, MATLAB is visible.
Yes, sir.
So let us see the same example. Let us define S as transfer function. Then I will take the open loop transfer function as 100 divided by s plus 1, s plus 2, s plus 3. Like this. This is open loop transfer function which is given. Open loop is stable. Okay. And let us check the closed loop. So what I will do is I will use this transfer function as g. It is g divided by 1 plus gh where h is 1. And I'm using some keyword called mean real. Okay, which will minimize the realization. Okay, minimize the realization means it will cancel out the common terms, everything, and it will give you the final transfer function. So the closed loop transfer function of this given OLTF is OLTF2 divided by 1 plus OLTF2. That is g divided by 1 plus gh. So we get this transfer function. Then I will find out the zeros and poles of this transfer function using again another keyword, zeros comma poles equal to transfer function to zero pole form. This is a keyword function. So I will use transfer function to zero pole form and I will only write the coefficients of numerator and denominator. So coefficients of the numerator are 100 and the coefficients of denominator we should start from the highest power of s, that is 1, 6, 11, 106. Then close the bracket and enter. So it says zeros. There are no zeros obviously because there is no polynomial in the numerator. And the poles. So poles are, there are 3 poles and out of 3, 2 are having positive real part. So the closed loop transfer function is having 2 poles which have positive real part or two poles which lie in the right half of S plane. Therefore, ultimately the closed loop system is unstable. And what we got, okay, what we got in the answer is also the same thing. Z is equal to 2. Okay, therefore there are two encirclements. So it's a Nyquist plot is like very nice thing. It requires some time to correlate the hidden mathematics behind the graph and the actual thing. But finally it is giving us the same answer, so we are in the right track. Fine. If anybody has any queries, those who are understanding, please stop me. Remaining can just watch out. So next I will take a second numerical with the same transfer function but with a less gain. So with the highest gain 100, we got unstable result. Let me reduce the gain to 10 and let us plot for the Nyquist plot. Okay, let us go for the Nyquist plot. So what is same here? P is 0, that is same. Fine. Then the location of poles is same. Then path AB we have to map. So we get GH of j omega, the magnitude as 10 divided by 6 instead of 100 by 6. So everything else is same except the gain. Therefore, I will just compare and modify the appropriate things. So 10 by 6 instead of 100 by 6. Angle is 0 degree, so A dash is A dash. Clear? There is no difference with the phase angle expression. Then we have 0, A dash, B dash same. Then let me consider BCD. So for this numerical, path BCD is somewhat like this, 10 divided by r cube e raised to j3 theta. So 10 divided by infinity cube is 0, whereas theta is again minus 270, 0, 270, same as previous. And path DA is again mirror image of path AB. So only difference is because of this gain, these gains will change. Only the starting gain will change, to be precise. Not much difference at all. The shape will remain same. So when the starting gain changes, let us see what it was 100 by 6 here. Now it is 10 by 6. So when the starting gain changes, everything else remains same. We can draw the same shape without any hesitation. Let us see how the starting gain or reducing the system gain has affected the stability. So again, we need to find m for this also, okay, that we don't know. So we will straight away follow the previous method to find m. That is, we know that it intersects with minus 180 degree line. So equate that to minus 180 degree line. Then after equating, solve for omega. Now I will call this particular omega as omega p. Omega p, which means phase crossover frequency. So whenever it cuts a minus 180 degree line, in control system terminology, we call it as phase crossover frequency. So find that phase crossover frequency. So instead of solving this lengthy expression, I will use a shortcut method. I will type the equation as it is, tan inverse x plus tan inverse x by 2 plus tan inverse x by 3 equal to 180. Then press shift, press calc, press shift, press calc again, we get omega equal to 3.316, which is nothing but square root of 11 only, approximately. So now gain at this omega we need to find. Okay, gain at omega PC. So do you think the value of m will change now or will it remain same? Anybody saying there is a change? Please respond. The value of m will change. Anybody thinks that value of m will change? Anybody wants to say the value of m will remain same?
Sir, M will change.
M will change. Anybody else want to say m will change? Okay, let us see whether it will change or it will remain same. So let us calculate the gain at omega p. So value of gain will now be 10 divided by, okay, square root of 12, 15 and 20. Okay, because this is omega square plus 1, this is omega square plus 4, this is omega square plus 9, therefore 11 plus 1, 11 plus 4, 11 plus 9. So value will change. Now we got 0.166. So that is magnitude of m is less than 1. Less than 1 means this m will be obviously before this minus 1. So we have to locate 0.166 approximately. Somewhere here I have located. Therefore, there are no encirclement at all. Minus 1 will remain outside. So P is 0, that is equal to P plus N, therefore 0 plus 0. So closed loop system is stable. Closed loop system is stable. So let us quickly cross verify in MATLAB. So we have 10 divided by s plus 1, s plus 2, s plus 3. And its closed loop transfer function is ten divided by s cube, 6s square, 11s plus 16. Okay, so it has 3 roots and all 3 are lying in the left half of S plane. Minus, minus, minus. A pair is a complex conjugate. So this is a proof that all 3 lie in the left half of S plane. So the gain is reduced, poles are retained in the left half. So try to correlate this with the root locus. So gain is less, roots are in the left half. Gain is increased to 100, roots have moved to the right half. 2 roots, okay, which followed 2 asymptotes have moved to the right half. So that is one correlation. You can do it later. Okay, with this, I will conclude the 2 numericals and I will briefly introduce, in detail I will introduce before solving more numericals. Let us understand what is stability margin. So this is the right point to introduce stability margin. So when system gain was 10, k equal to 10, the closed loop system is stable. And when it was 100, the closed loop system was unstable. Unstable. Fine. So now the question is, till what value of k the system, the closed loop system is stable between 10 and 100? So that is certainly a question for everyone. Suppose you are riding a bike and you are doing its mathematical analysis and you end up with, while riding 10 kilometers per hour, your mathematical analysis says it is stable. And while you are riding at 100 kilometers per hour, your mathematical analysis says it is unstable. So obviously we will have a question till what speed I can ride so that it will remain stable. That is what system gain. So is it 20, is it 30, is it 50, or is it 80, 90? Which is the limit for stability? What is the limit for stability? So we have that question. So this is answered by a terminology called gain margin. Okay, this is answered by a terminology called gain margin. Okay, so what is gain margin? What is the definition of gain margin? Let us see. So gain margin is a multiplication factor by which the existing gain must be increased must be increased to make the closed loop stable system. Please remember, to a closed loop marginally stable system. So what is that multiplication factor that you want to multiply so that a stable system will become critically stable or marginally stable? So let us see how that is given. So for this particular example, the closed loop system is stable because there is no encirclement. So if suppose you go on increasing the gain, somewhere it will reach -1. Okay, somewhere it will reach -1. So let us see how that can be interpreted in terms of gain margin. So now my question is, you have, say, gain M at -180 degree line. Okay. Suppose you have increased gain now, system gain, and this is how you got the curve, critical stability curve. So from 10 to 20 to 30 to some value x. So my question is, at what value of system gain do we reach gain equal to unity? Okay, at what value of system gain do we reach this gain equal to unity or m equal to unity? So at k equal to 10, obviously we have not reached the -1.8. At k equal to 20, we are not sure. At k equal to 30, we are not sure. I mean, not sure in the sense, I'm increasing the gain. And as I increase gradually, at some point, it will reach the -1 point. And after that gain, it will enclose the -1 point and it will become unstable. So my question is, what is that value which makes this curve just to enclose -1 point so that n become equals to 2 and z become equals to 2, the closed loop system becomes unstable. Okay, and critical stable means it doesn't enclose or it doesn't keep it outside. The curve is just moving on -1. So that is called as critically stable. So my question is, we have m at k equal to 10. For this present example, we have m k equal to 10 and that m is 0.166. So with what value I should multiply to this m such that I will get m into that multiplication factor equal to unity. Okay, with what factor I should multiply to get this total m equals to 1. So very straightforward answer. If you multiply it with 1 by m, you will get equal to unity. So this 1 by m is called as gain margin. Okay, 1 by m is called as gain margin. I hope everyone is following this. I will repeat the concept. I want to know, okay, I want to know for which open loop gain this curve just crosses through -1. Okay, for the present example, it is already stable for k equal to 10. But if I increase speed to 30, will it enclose or no? If it doesn't enclose, then don't worry, it is stable. If I increase the speed to say 40 kilometers per hour, then will it enclose -1 or no? If it encloses, then it is unstable. If it doesn't enclose, it is stable. So like that, I want to check. Okay. So for this present example, now k is 10. Then what is the factor that I can multiply with that k such that my curve just passes through this -1? So let us see quickly. I told 1 by m is the factor which you can multiply with the existing gain to make the system just critically stable. So what is that value we will get? So as of now, understand 1 by m is our gain margin, and gain margin in decibels is in the log scale is given by gm in dB equal to 20 log 1 minus 20 log m is equal to 0. So minus 20 log m is the gain margin in dB. So gain margin in dB, this is the formula. Fine. So this is the formula for gain margin in dB, where M is gain at phase crossover frequency. So gain at a frequency which cuts minus 180-degree line. So for this present example, let me show you the gain margin. Okay, so gain margin, I said it is 1 by M. Okay, please understand the definition of gain margin again. It is the multiplication factor by which the existing gain must be increased to make the stable system to marginally or critically stable. So keeping in this mind, we'll study the gain margin for this particular system. So Gm equal to 1 by M, and this M is 0.166. So what is 1 divided by 0.166? So it is 6, approximately 6.0. Now, what is the existing gain? Our existing gain is 10. And what is the gain margin? It is 6. So you can multiply the existing gain by 6.002, or multiply by 6 times, or increase by 6 times to make this stable system, this particular stable system, to a critically stable system. I repeat once again, gain margin is a multiplication factor by which the existing gain can be increased to make a stable system to a critically stable. Okay, so this is a stable system already, and it has a gain equal to 10. So till what value I can increase? So that system will just become critically stable, and after that it will become unstable. So for that question, answer is given by gain margin. So what the gain margin tells is, you can increase the existing gain by 6 times, that is 10 into 6, 60, such that your system will become a critically stable. And if you increase by 7 times, it will become unstable. Is it a nice mathematical tool? Okay. So your bike is running at 10 km per hour, and you do some mathematics and find out you can increase by 6 times. It means you can ride in a stable zone up to 59.99 kilometers per hour. When you start riding at 60 kilometers per hour, it is critically stable. Which means if you ride it by 60 point, say 5 kilometers per hour, you will lose the control. And if you ride it at 39.99 kilometers per hour, you are safe. So this is a critical boundary. Gain margin gives us critical boundary. So finally, gain margin in dB is given by minus 20 log m, minus 20 log m. So minus 20 log m is 0.166. So if you multiply using log, you will get 15.56. So in decibels, it is 15.56. In magnitude, it is 6.002. Okay. So here it is a magnitude, you have to multiply with magnitude only. Don't multiply 10 with 15 because they are on different scale. Fine. So for stability, the gain margin is always positive. For stability, the gain margin is always positive. So what I meant to write this last sentence is, a stable closed loop system will always have a positive gain margin. Okay, an unstable system will always have a negative gain margin, which means this curve has already encircled minus 1. So that's why you end up with 1 divided by say 1.5. Okay, 1 divided by 1.5, and you will get a gain margin lesser than 1, which means you have to reduce your speed. Okay, and minus 20 log of 1.5, you end up with a negative value here. So an unstable system which has encircled the minus 1 will give us a negative gain margin in dB. Okay, so in dB, for a stable system, we should always have a positive value. Okay, so that's it for today's class. Any queries, any doubts anybody has? Please go through the videos without fail. Mr. Hruday R. Have you followed today's class? Yes. Okay, Shweta.
Yes, sir, follow.
Okay, I hope I am able to convince this. You have to watch the videos again and again to make things more clear. Mithun Bhatt, Nadim Sharif.
Followed, sir.
Okay, fine. So please raise your queries if you have anything in the before proceeding the next class. So we are done with one of the stability margin now. There is the second stability margin which is called as the phase margin actually. There is a second stability margin which is called as okay. So there are two stability margins. The first one is gain margin. Second one is phase margin. Okay, that we will do in the next class. So it is related to phase angle now. So we dealt with gain now. It is related to phase margin. Okay, fine. So thank you one and all. Bye.